United States Department of Agriculture.
So thank you so much, everybody, for attending today and for sticking around till the end. So today I'm going to be talking to you about basically refining methods of euthanasia for laboratory rodents. And this is an area I've been working on for quite a number of years now. And hopefully we all agree that it's a really important topic. So I'm not going to go into this in huge detail. I'm sure you're all aware that rodents represent the most widely used species for biomedical research globally. So just to kind of highlight the scale of the numbers, we're talking about approximately 190 million rodents used every year, and that's a very conservative estimate. And unfortunately, a prerequisite to their use is that they often have to be humanely killed at the end of the scientific work. Now, this is obviously due to several reasons. Often it's because they've reached the end of the study, and therefore scientists need their tissues, for example. But also generally, at least in the UK, reuse is not really permitted without special permissions. It can also be because they're surplus to requirement, such as at the end of their breeding life, or indeed if you have a breeding colony, you might have an undesired genotype, so often they do get killed at the end. And also it can be to end unnecessary suffering, so if we have, for example, have reached a humane endpoint. And therefore what I really wanted to highlight here is that it really does therefore represent the most widely used procedure. So worldwide, euthanasia of research animals is regulated by different legislation or national guidance. So in Europe, this is mandated by Directive 2010/63/EU, which was transposed into national legislation of those members of the European Union. And in the UK, that is transcribed as Schedule 1 of the Animals in Scientific Procedures Act. In the US, you obviously have the AVMA guidelines for the euthanasia of animals. And similarly in Canada, we've got the CCAC guidelines. And we also have similar guidelines in countries such as New Zealand and Australia. However, one of the shared aims, despite obviously having different regulation and guidance, is that they all share the vision of ensuring that animals are killed with minimal pain, suffering, and distress. So what I wanted to just do here is to demonstrate that there is obviously discrepancies in terms of what methods are permitted according to what country you're in. So green is permitted methods, orange is permitted with additional permission, and red is not permitted. So as you can see, it really does depend upon where you are. And therefore it does represent the fact that there's no consistent method adopted internationally. And therefore, I really just wanted to pose the question as to whether we think this is acceptable. Should we have much more cohesion? Should we all kind of be learning from each other? So there's lots of obviously different permitted methods, which often don't form part of the harm-benefit analysis when we're ethically reviewing the programme of research. A lot of focus tends to be on how are the animals kept and what are the harms associated with the scientific procedures. And particularly in the UK, therefore, the humane method of killing doesn't formally form part of that harm-benefit analysis. And therefore, it got me thinking, is that acceptable? How do we decide which method is the most humane, whilst also balancing other factors, such as the integrity of the scientific study? So, for example, we might think overdose of anesthetic is the most humane, but it obviously has chemical properties and therefore it could confound your scientific data at the end. So in that situation, what do we do then? So it is really multifaceted. Decision is often more complicated because we do have to balance animal welfare, but also the scientific outcomes. And also, unfortunately, we can't overlook certain practical constraints such as time and cost. So aside from the requirement of some of these methods to be used with additional permissions in some countries, the most commonly used methods, at least in my experience, are cervical dislocation, striking the cranium or blunt force trauma, decapitation, overdose of an anesthetic, and exposure to CO2 gas. And therefore what I wanted to do in this talk is to summarise the existing research that has focused on assessing whether these methods are capable of providing a humane death, before then moving on to more recent work that we've been looking at to try and refine some of these methods. However, and in line with Megan's presentation over the break there, one thing that we cannot overlook when we consider these methods is that selecting an appropriate method does not just rely on the welfare consequences to the animal, but we've also got to think about human well-being. So from the animal's point of view, and determining their welfare during the killing process, we obviously can't ask animals how they feel or what they've experienced, and therefore we've got to think about how we can effectively assess their welfare doing so during the killing process. So a lot of methods aren't instantaneous, and therefore we've got to consider what happens to them before they lose consciousness. So in order to scientifically determine an animal's welfare, we have to consider the time that it takes them to lose consciousness and their potential to experience negative experiences during their conscious phase. And therefore we can look for evidence of these negative experiences, such as pain, anxiety, or stress, and we can employ things such as drug interventions or pharmacological interventions to determine whether these actually change the results in terms of their behavioural responses or indeed physiological responses. And therefore, what we've been doing over the past few years now is taking a multifaceted approach, looking at behaviour, physiology, and also pharmacological interventions in order to tell us more about the animal's welfare. So as I mentioned, and I'm not going to go into this in much detail because it's not my area of expertise, but I just wanted to kind of highlight that we also have to consider the impact on the human operator, which has been a real focus in recent years, specifically looking at compassion fatigue across the sector. And I know a lot of research now is coming out showing that physical methods of euthanasia, such as cervical dislocation or decapitation, are actually associated with greater likelihoods of the operators experiencing compassion fatigue. So going into some of the permitted methods, I just wanted to give obviously a brief summary of what they are, the mechanism of action, and then briefly in one slide summarise the state of the current literature. So cervical dislocation involves the separation of the cervical vertebrae, which results in lethal trauma to the spinal cord. Its onset of death is rapid unconsciousness due to concussion, damage to the brain, and/or cerebral ischemia. Now, a lot of people have different approaches, and this is something that I'm actually in the process of looking at the moment. So we've got some experiments running this week and next, looking at different kind of techniques that people use in order to achieve that cervical dislocation. So some people will use their hands without a tool. So that's what we refer to as manual, versus some people will employ things such as a metal rod or indeed a specialist tool that they've kind of come up with at their institution. So when we're talking about mechanical, I mean people using a tool. Now, of course, for the operator and indeed for kind of public perception, it's aesthetically unpleasant. However, I guess it does have advantages due to the absence of administering chemicals, and therefore it does have some benefits for scientific data outcomes. However, at the moment, there is actually very little scientific evidence showing that it offers a reliable and/or a humane death. So just to summarise some of the work to date, the data, when you delve into it, actually is largely extrapolated from work done in rats where they looked at decapitation. And this work raised concerns about the accuracy and efficacy of the location of the dislocation. So obviously, mice and some rats are particularly small, and therefore previous work has shown that there are relatively high failure rates. So it was reported that nearly a quarter of mice exhibit thoracic rather than cervical fractures, and therefore this really does affect their welfare at killing and how quickly they will lose consciousness and die. Essentially, for an effective dislocation, you want a really high cervical dislocation in order to ensure rapid concussion, neurogenic shock, unconsciousness, and death. However, having said all that, if it is done correctly, it can result in quicker loss of cortical activity and brain death compared to decapitation. So decapitation obviously involves the total separation of the head from the body, and its mechanism of action involves the loss of brain function due to ischemia. Often people have dedicated guillotines for both rats and mice. However, again, a really practical thing to consider is that blade has to be properly maintained to ensure it's sharp and functional. Again, it's aesthetically unpleasant. And once again, similar to cervical dislocation, it doesn't involve administering any chemical compounds, and therefore it is attractive if you don't want anything to impact your scientific outcomes. However, again, when I delved into kind of the scientific evidence base, its capacity to ensure a humane death does remain controversial. And this is largely due to work done by McKesker and colleagues in 1975, so quite a while ago now, who showed that mice showed sustained brain activity for around 14 seconds after decapitation, and brain death didn't occur till 27 seconds. However, other people have argued that due to rapid blood loss, it's likely that this would result in hypoxia and unconsciousness in less than 2.7 seconds. Subsequent electroencephalograms, so EEG looking at brain activity, has suggested unconsciousness around 3.7 seconds and brain death took 17 seconds. So I guess to summarise decapitation, although it is highly effective for inducing a non-recovery state, and we know they can't recover from this, EEG data suggests unconsciousness ranges between 3 and 40 seconds. And therefore, for me as an animal welfare scientist, I think until conclusively proven, a conservative approach is to use the upper durations for loss of consciousness in order to form conclusions about the technique's ability to induce a rapid and humane death. Moving on to concussion of the brain. So this describes a method whereby a severe blow to the skull is conducted with sufficient force to produce hemorrhage and depression of the central nervous system. It results in rapid acceleration of the head, which causes the brain to impact in the inside of the skull. This disrupts electrical activity due to changes in intracranial pressure and also damage to blood vessels and nervous tissue. Once again, this is aesthetically an unpleasant technique, and we did a recent survey last year across UK institutions and people working across the sector. We actually found that a very small percentage of people are still utilising this technique, and I suspect this is because of kind of the negative perception that it does have. However, similar to the other two physical methods, it does obviously have its advantages in terms of an absence of toxicity. So I've kind of given away the game here already, my next slide, but at the moment there's no direct scientific evidence in laboratory rodents showing a reliable or humane death for the method of concussion of the brain. So I'm quite surprised that it's not really been studied specifically in laboratory rodents, and therefore when we consider its ability to be humane, the more sensible kind of approach is to look at evidence to extrapolate from other species, such as agricultural species. Obviously, most farm animals are stunned prior to slaughter, especially poultry, for example, and therefore they probably provide the most meaningful comparison when we're thinking about laboratory rodents. Obviously, in the agricultural sector, there's a range of specialist devices, such as non-penetrating captive bolt guns, which are then immediately followed by exsanguination or cervical dislocation. However, to date, at least to my knowledge, there's no specialist equipment available to deliver a consistent concussive blow to laboratory rodents. I have heard of a couple of groups presenting at conferences looking at similar concussive devices that are used for things such as poultry, in rats, for example, but I haven't seen it actually showing much success. Moving on to overdose of anesthetic. Generally, this falls into two categories, so barbiturates and halogenated anesthetic gases. Barbiturates, such as sodium pentobarbital, at least in the UK, I'm not sure what it's like in the States, are the most commonly used anesthetic for euthanasia, and they're usually administered in large doses via the intraperitoneal or intravenous route. However, obviously, we have to consider the effects of the compound and its ability to confound scientific data. However, it is often considered gold standard, but I think it's important to highlight that unlike physical methods, the transition to unconsciousness is much longer, so loss of consciousness ranges between 104 to 140 seconds. And once again, when we look at the literature, there's not a whole lot been done so far, and therefore scientific evidence showing it offers a humane death is currently lacking. There has been some evidence to suggest that rodents experience pain and/or discomfort following an injection, And this is likely due to the fact that sodium pentobarbital is highly alkaline. It's got a pH of around about 10. And this has also been demonstrated by upregulation of the early gene marker CFOS in the spinal dorsal horn, which has been taken as indicative of greater pain in these animals. There has been some evidence suggesting that administration of local anesthetics may reduce pain in rats. However, given we know that the efficacy of local anesthetics generally is a couple of minutes, the mechanism of action actually remains unknown. So we don't know why they may show reduced pain, given that the compound itself would take several minutes to have its effect. And often what people have done is combined the local anesthetic with the pentobarbital, so they've not administered it before. And again, another consideration with an overdose of anesthetic is when we're talking about euthanasia methods, we also have to not just consider the welfare due to the application of the killing method, but we've also got to think about everything that happens to that animal before it loses consciousness. And example for overdose of anesthetic is that they have to be handled and restrained, and therefore this could increase their stress levels. So at the moment, there's limited scientific evidence to suggest that local anesthetics could offer refinement in rats, but this does still need to be investigated in mice. Finally, in terms of the permitted methods, we've got exposure to a rising concentration of carbon dioxide gas, and this does remain one of the most commonly used methods. I think there is a slow transition that I've heard of, at least in the UK, of people moving away from CO2, but generally it is still widely used. And obviously this is probably due to it being the only method available to people at the moment that is capable of high throughput and also a non-contact approach. So you'll all probably be aware there's a lot of different systems that are commercially available. Some are fully automated, some allow the animal to be euthanized in its cage with its cage mates, while others, and they definitely exist over here still, rely on the operator removing the animal from the home cage into a dedicated gas chamber. So that's a much more kind of manual system. So its mechanism of action is due to hypercapnic hypoxia. So you obviously get hypoxia due to the influx of CO2. It results in neuronal acidification and also reduced intracellular pH. And I think we'll all probably be very aware that there's a lot of evidence now showing the negative experiences of animals exposed to CO2, and therefore there is concern for its continued use for animal welfare. So I'm not going to even try to kind of summarize all the work that's been done in this area. So just to kind of put up a few key papers and reviews, there's quite a few reviews out there now. Essentially, all the data suggests at high concentrations, rodents are capable of experiencing pain, and also things such as anxiety, distress, and breathlessness as well when exposed to CO2. So I guess some people might be thinking, okay, so if pain is associated with high concentrations, is that not avoided by gradually filling the chamber? So gradual fill was mandated across the EU by Directive 2010 to try and avoid CO2 concentrations that are capable of causing pain. So the animal essentially enters an empty chamber that's not pre-filled, and obviously the gas is then employed. The recommended guidance in the UK is to fill the chamber at a lower flow rate than that's recommended in the recent edition of AVMA's guidance. So typically we fill at a 20% chamber volume per minute, whereas that's much higher across the US, so it's 30 to 70%. And this was obviously changed because it's thought to achieve a balance between rapid unconsciousness with minimal distress. And therefore, again, it nicely highlights that although we're all working in similar areas with the same species, there is this kind of lack of cohesion internationally in terms of how we are doing these euthanasia methods. So kind of fill rate aside, one thing that we have found in our recent work is that given the properties of the gas, including their densities, are dependent upon the concentration inside the chamber, it's not just reliant upon how quickly you fill the chamber, but it's also a case of where you fill that chamber. We actually found some quite striking data here. So essentially, because CO2 is heavier than air, good practice is considered to fill the gas from the top, so then you get a more even dissipation of the gas throughout the chamber. Whereas if you fill it at the bottom, there's a greater likelihood that you get in higher concentrations of CO2 at the level of the animal. So what we found in this particular study is this is just CO2 concentration across time, but you can clearly see if you bottom fill the chamber with CO2, you are getting much higher concentrations sooner than if you top fill, and therefore it's possible that by bottom filling, mice or rats are being exposed to high concentrations which are capable of eliciting pain. So in terms of the sort of timeframes that we're thinking about when we're thinking about rodents being conscious when they're exposed to CO2, our recent work focused on looking at brain activity and the transition towards unconsciousness when mice were exposed to CO2 compared to our novel method, which I'll come on to in a couple of slides' time. And we're talking about approximately a 2-minute period. So it's not a quick method by any means, but obviously that is with the caveat that we are doing it in line with UK regulations. So that is a lower flow rate compared to the States. However, what was really interesting from our work is also that loss of posture, so when the animal becomes recumbent, was actually occurring much sooner than their brain activity was showing loss of consciousness. And therefore, for me, this raises concerns that the animal is simply incapable of moving, and we're sometimes increasing gas levels at that point. And therefore, there is the possibility that they are fully conscious still at relatively high concentrations of CO2. So with all that kind of in mind and a bit of a kind of whirlwind summary of the current state of the literature, I just kind of wanted to put a bit of a provocative question about whether we still think all permitted methods are humane and where can we go next? How can we make refinements? So one thing that I get asked a lot is, okay, so CO2 is clearly bad because of the CO2. They can detect it. It's capable of activating nociceptors in the mucosal membranes. What about an inert gas? And I think this largely comes to Dr. Mohan Raj's work at Bristol, whereby he exposed pigs eating apples to either CO2 and argon, and you'll see the clear differences in behaviour. So just hopefully these work. So this is with CO2. You can see the pig is really reluctant to go back for its apple, not up for being in there at all. Whereas for the argon, I'm just going to close that one. For the argon, you see a very kind of different behavioural response. So quite happy eating away there. And obviously didn't detect the gas, became hypoxic, and ataxia set in. And then I think it shows you at the very end, despite becoming ataxic, just decides to go back for the apple. So yeah, I get asked a lot about inert gases such as argon and nitrogen. And I think it could be because in some species, obviously it has offered a potential refinement. However, previous work has looked at this in laboratory rodents and unfortunately found that rodents also find inert gases aversive, such as argon and nitrogen. They will actively avoid a chamber filling with these gases, and this has been kind of highly reproducible across groups as well. In terms of an alternative gaseous compound, again, people often consider isoflurane, and there is some evidence to suggest that it does offer potential refinement, although also some evidence demonstrates that it's equally as aversive. However, one major kind of limitation of its potential is that rodents often show greater aversion to isoflurane if they've had previous experience of it. So for example, if you've got a surgical model that's obviously undergone isoflurane anesthesia, they will show greater aversion during euthanasia. So that is something that unfortunately has to be considered if we are thinking about this as an alternative method. So for the past 5-6 years now, we've been obviously looking at refining rodent euthanasia. And the project that I was working on in Glasgow as a postdoc was investigating the potential of hyperbaric hypoxia via a process referred to as gradual decompression in order to provide a humane alternative to CO2. So essentially, we wanted to look for a novel method that's also capable of high throughput killing and also offers human operators a kind of non-contact, hands-off approach. So essentially, what is decompression? So gradual decompression describes a process similar to ascending to a high altitude, and as such, it results in hyperbaric hypoxia. Hyperbaric hypoxia occurs because as the atmospheric pressure falls, there's also a proportional decrease in the partial pressure of oxygen. And as such, this is why people climbing Mount Everest, for example, often need supplementary oxygen. And the reason it's become particularly attractive is because in humans, so for flight crew, they often have training to simulate this hypoxic state. They report that they don't know they're becoming dangerously hypoxic before they ultimately transition into unconsciousness. And if they don't obviously get supplementary oxygen, they would die. So I didn't have time to go over all the data that we found, so I just wanted to kind of give the key findings. So we found that decompression, despite taking longer for them behaviourally to lose posture, the mice during this kind of longer induction time are performing relatively normal mouse behaviours. So they're spending time grooming, they're rearing, they're digging, and they're exploring their surroundings, which is very different to a comparable situation with CO2. So we always did our experiments as a comparison with CO2. With CO2, in line with the literature, had greater gasping, which interestingly was also mitigated through analgesia, which is really interesting from a breathlessness point of view. And we also conducted an experiment looking at brain activity via EEG data, and we actually found that this gasping behaviour is happening during the conscious phase and therefore could indicate greater respiratory distress. With decompression, it's very different. I'm hoping the paper will be out soon on this. But essentially, with decompression, there's a really different pattern of activity that's happening in the brain. There's a really gradual transition to unconsciousness, whereby the mice aren't fully unconscious, but they're very much bordering that line. And therefore, it's likely illustrative of cognitive impairment. Again, we know from humans that when they become hypoxic, they can't perform simple tasks. So we think what we're seeing in the brain activity also represents a similar situation with the mice. And this is happening considerably before the animal loses posture and consciousness. And therefore, at the moment, we're concluding that it's likely that the animals therefore have reduced perception of potential negative sensations. So I'm aware of time, so I'm going to wrap this up really quickly. But essentially, the work has been really positive so far. It's very much an ongoing body of work, but at the moment, the evidence suggests that it could offer major refinement. As such, it could have direct implications for policy and national guidance. And we also have a PhD student at the moment at Newcastle University, Sophia, and she's going to be looking at its potential in rats as well. So at the moment, the evidence is just focused on mice. So we will be continuing that to look at its potential in rats. And very quickly, kind of given my review of the literature, I wanted to also look at different methods of cervical dislocation. So I conducted a survey this year, trying to get at what people are actually doing when they're cervically dislocating, because I have seen all different people using all different tools and techniques. And then what we're doing at the moment is experimentally assessing the four most common methods. And we're looking at not just the behavioural responses, but also we're looking at where we're actually getting dislocation. And we're going to map that to the behavioural responses via CT. So that's very much ongoing at the moment as well. So with that, obviously, it's a big body of work. So it's not a single kind of effort. So I'd like to thank all the collaborators and funders, and also thank you so much to the organisers today for such a great event. So thank you very much.
USDA is an equal opportunity provider, employer, and lender.